Welcome to the Explainer. So, you've got a critical piece of equipment and it just starts failing. Out of nowhere. The likely culprit? And an invisible enemy, electronic noise. Today, we're going to hunt it down. We're going to build a digital trap, step by step, to make this invisible problem finally visible and solvable.
Okay, let's dive right in. We're going to follow this builder's journey. We'll start with the problem itself, and then we're going to keep adding layers of realism to our simulation. You'll get to see how a really simple model can grow into a full-on professional-grade tool.
You know, our whole journey here really kicks off with a plea for help. It's a scenario it's painfully familiar to any engineer who's dealt with a frustrating and really expensive mystery, right? This is such a classic engineering headache. You're just swapping out this expensive hardware, which is really just a Band-Aid, not a cure. You're bleeding money because the root cause, that invisible high-frequency noise, it's still there. So the real question is, where do you even start?
Well, you definitely don't start by just guessing. Instead of burning through time and money on physical prototypes that might fail anyway, you build a digital playground. The whole point is to make the invisible visible. But first, you have to be really clear about what you want that playground to actually do.
And this, right here, is the key insight. The goal wasn't to build a perfect one-to-one digital twin of the thing. No. It was to build a model that was just good enough to show the behavior and the trends of the noise. The simulation is for understanding the why. The physical hardware test, that's for proving the what. And that simple distinction, it saves an enormous amount of time.
So let's start building. You don't try to model the entire super complex system all at once. The first step is to create a simple but really powerful foundation that captures the core physics of the problem.
Here it is. This is basically the recipe for our base model. But the most important part here is step 2. Key parameters are designed to be adjustable. You know what that means? It means an engineer can test different countermeasures in seconds just by changing a line of code, instead of spending hours with a soldering iron.
So the model is actually built to intentionally create this ringing, that unwanted vibration you see in the electrical signal. This is the digital fingerprint of our noise problem. We create it by adding these tiny, what we call parasitic effects. You know, the unavoidable extra inductance and capacitance that comes from real-world wires and components. Now, our simulation speaks the exact same language as the failing hardware.
Okay. That single-phase model is fantastic for getting a handle on the basic physics. But most industrial stuff, like the machine from our original request, uses a more complex 3-phase setup. So yeah, it's time to level up our simulation.
Now, the really clever part is that you don't have to start from scratch. You just take our proven single-phase building block, you copy it twice, and you just offset the timing. It's a really elegant way to scale the model's complexity to perfectly match the 3-phase system that's being used out in the field.
Okay, so our 3-phase inverter model now works just like the real thing. But that also means it's, well, leaking all that high-frequency noise out onto the power lines, and that can mess with other equipment plugged into the grid. We need to build a digital shield.
The answer is an EMI filter. Now, EMI just stands for electromagnetic interference. The easiest way to think of it is like electronic static that pollutes the power lines. This filter isn't just one part. It's a small team of components, and they all work together to trap that noise before it can escape.
And each part of our digital shield has a very specific job. The X capacitor, it works across the power lines. The Y capacitor acts like a little drain, safely sending noise down to the ground. And the common mode choke? That's the bouncer at the door, physically blocking that high-frequency noise from getting out. By tweaking each of these in the simulation, you can design the absolute perfect defense.
So now we've got this fantastic model that simulates the inverter and its filter. But to turn it into a true professional-grade tool, one that can predict real-world performance with high confidence, we need to bring in 3 more critical factors. This is the final upgrade. This is what takes it to a pro-level tool. We can now import digital models for specific, real-world parts. We can simulate how things perform in extreme heat and cold. And what's really important, we can test for regulatory compliance using a listen. That's a special device to measure noise. And check it against standards like CISPR 11, which is basically the official rulebook for this stuff. And this workflow just puts it all together.
You can see how one specific part behaves at scorching hot temperatures and then instantly know if it's going to pass those regulatory tests, all before a single physical part is ever even ordered. That's powerful.
And it all comes down to this. That abstract rule buried in some thick regulatory book becomes one simple number right here in our simulation. The model measures the noise in decibel microvolts, and the result is just a clear, simple answer: pass or fail.
So let's just step back for a second. We started with this really frustrating mystery, and just step by step, we built a seriously sophisticated engineering tool.
What we've really done is create a digital microscope. We've transformed a problem you literally couldn't see into something you can measure, you can analyze, and you can defeat. The unsolvable has become solvable.
You see, this model isn't the end of the journey. It's really the beginning of yours. It's a launchpad for testing new ideas, for trying out different components, for designing better solutions. We've shown you how to see the noise, so the only question left is, what will you build?